Okay, so good day everyone. Our topic for today is about Introduction to AI and Intelligent Systems. As Herbert Simon mentioned, he stated that it is not his aim to surprise or shock you, but the simplest way he can summarize is to say that there are now in the world machines that can think, that can learn, and that can create. Moreover, their ability to do things is going to increase rapidly until, in a visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. Intelligence is the ability to understand and learn things. Intelligence is the ability to think and understand instead of doing things by instinct or automatically. In order to think, someone or something has to have a brain or an organ that enables someone or something to learn and understand things, to solve problems and to make decisions. So we can define intelligence as the ability to learn and understand, to solve problems, and to make appropriate decisions. Artificial intelligence is an applied subfield of computer science, which is a combination of computer science, physiology, and philosophy. Artificial intelligence is a very general investigation of the nature of intelligence and the principles and mechanisms required for understanding or replicating it. To give us more details, I will share to you a video presentations on the introduction of intelligent system. So if you have some questions related to the question, do not hesitate to post your question in our chat box for me to address your queries or your comments.
If you have followed the Introduction to AI course, so familiar faces, and I'm a familiar face. I'm going to teach this class together with Michael or Michael. This guy, he's going to take over the parts on machine learning and reasoning with uncertainty. And I will talk about the state space representation and search part, and at the end about the logic part and knowledge representation. The course, of course, is not taught by two people, it's taught by a whole group of people, and these are the names in alphabetical order, apart from some mistakes I made in the ordering of the people who help or are also involved, and these are all the TAs that you're going to see, or some of them you're going to see. Today is the first lecture, and the first lecture is obviously an introduction to the topic so that you have an idea of what to expect from the course. It's also an introduction to what you have to do in order to get the grades for the course. And I also want to start with parts of the technical material. So Introduction to AI was a general overview, getting the ideas, getting some first insights into some of the algorithms. And now we really try to systematically get you to understand the idea of how to build an intelligent system, how to build an intelligent agent, the first AI that you're going to build. As you can see, I'm trying to record the lecture, and I will put it online, try within 24 hours a link on YouTube, so that you can see what I try to explain. Look at it again, look at it in half speed if you want, look at it in full speed if you want, double speed. You even get subtitles from YouTube, so that's really very cool. So we already have recordings from last year, so they cover more or less the same material, but in different orders and different, also different depth, because it used to be a second-year course. So the link has been provided. You can already look at it in advance. Please do so, because then you can follow the material more easily and you can ask questions if you want. So, I don't know what happened here. Let's do that again. So the course is taught by Michael and me, plus the TAs who you're going to meet. You're going to meet them on Thursday and Friday, depending on which group you are. There will be one working group in which we practice the theoretical material and prepare you for the exam. And there will be computer practica where you can get help if you want to. So you don't have to come to any of the lectures or working groups or computer practica, but where you can get help if you fail to do the worksheets that we provide on your own without help. And I should start with a word on the programming, because I understand that you have started with the first lectures in Python today or yesterday or maybe tomorrow. And if you look at the first worksheet, you will probably be rather shocked that there is already some programming we expect from you. And the programming that you would need in order to do all the exercises for this course are far more advanced than what you know now, or what you even know in the first 3 weeks or 4 weeks. So what we give you is not the task of implementing everything properly in the practical part of this course, but what we ask you to do is really do your best to try and do so. So I'll get to that back when we talk about the assessment of the practical part, but don't panic if you now see worksheets where you think, oh my God, I have no idea what the task is. We know that, and we take this into account. So the advantage of having this course now, directly after the introduction to AI, is that all the introduction that I did in the AI course, introduction to AI course, isn't needed anymore. So I just have a very, very quick repeat of what I explained in the first lecture. Now the question is, I started with the video of the series Person of Interest. Did anybody started to look into this series after the first lecture of the first period? Yeah, someone did? Still do, if you don't, but that's what I expected. What I want to remind you of is the story that is told there, and which I think is quite close to what we can already do, or quite close to reality. And that is that it's about a machine that is an intelligent agent that has cameras and microphones, sensors, and the only thing it has in the beginning as an actuator is a telephone, and it only gives back numbers. So it's a very intelligent machine that has very restricted input and output, particularly the output, I have to say. And the main task that it has to do is to classify whether ordinary people, are in danger of becoming the victims of the perpetrators of a crime. And then this crime is going to be stopped or not, and that makes it a sort of a watchable series. And these tasks of classification and decision-making are really central to most of the intelligent systems that we deal with in our daily life. And the tasks that you have to use are core AI tasks. So you need to do text processing, image processing, data integration, knowledge representation, automated reasoning, machine learning, genetic programming. These are all things that this machine does. And some of them we are going to look into in more depth. Some of them we don't. So this is not a course about image processing or data integration, and also text interpretation is not part of what we can cover here in this first course. But you will get courses later that cover, for example, text processing. What is, I think, common to what we are going to see throughout this course is the idea that this intelligent machine has the goal of performing optimal with respect to a set of measurements, some criteria, some expected outcome. And this expected outcome is to give as many of the social security numbers of the people who are in danger without giving any false warnings or so. So that is the objective that this machine has to solve. And what it does is to try to find the best estimate that it can get to give one of those numbers. There's no perfection involved. It just tries to get as much information from everyone. Is that science fiction? I don't think it is really. Of course, it is a bit exaggerated. We can't do that stuff, and luckily we can't do that stuff at the moment, also because the data is protected and so forth. But it is very close to the kind of complexity that we can deal with now, like the AlphaGo that you have all heard of now, the Google driving car, the Siri or Alexa language speech recognition. Or the more knowledge kind of AI, where a system can answer any kind of natural language question better than humans can. And it's not perfect what Watson does. I think that is clear from also the presentation that Chris gave. So Watson is also doing loads and loads of mistakes, but it tries to give the best answer to the question according to the means that it has, and that is data that it gets from sensors or and the reasoning capabilities that it has to give you the best prediction. So I showed you this this link to these the Google experiment pages, and I can really recommend you to look at, to go to this website and play around with some of these tools, because some of them are really, really impressive. So this one is one you need a camera. The camera takes a picture of any object, and Google tells you what this object is. And this is dramatically difficult, but we're nowadays so far that this can really be relatively reliably done by machine learning as a basis. And we're going to see that in the second part of the course, that how to do these, how to write these algorithms that can recognize these kind of images efficiently and effectively. The other part that is more where I do my research on is the knowledge part. And I think Frank gave a very good presentation here about it, that nowadays all the companies that, the bigger companies anyway, so Google, Microsoft, IBM, eBay, and so forth, you name it, they build their business models on the basis of knowledge graphs. I know it from Elsevier, I know it from Siemens, but I also know it from smaller companies, I know it from the governments, and so forth. So it's really has become one of the core knowledge representation means for businesses and public organization and so forth. And this creates enormous amounts of problem, because we need to organize this knowledge, we need to access the right knowledge, and so forth. And that, again, is part of what we need an intelligent agent to know and to be able to deal with. Very concretely, what we are going to do in this class and the sister class in period 6, so in June, is to address a problem that's called Schnapsen. And Schnapsen is an Austrian-Hungarian card game. It's a trick-based card game. So I think I have a Kahoot for this, and let's now see whether that, no, not a Kahoot, a Mentimeter. Let's see whether that all works. That was the idea, should be here. And here comes the first question. So if you would go to the menti.com, user code 778888, and then there are 4 options, and I'd be interested. Yes, are you rather good at Schnapsen? Yes, you've played it occasionally. You play trick-based card games, or you've no experience at all. Yay! Who's this one person? Where are you? So when we prepared the first version of this course 2 years ago, I regularly played this with my daughter, and I really, really like the game. It's very entertaining. It's a nice thing that you can play it with 2 players, and it has a lot of aspects to it. So I think it's clear that very few people have played it. I would really recommend you, and that's the homework that I give you for tomorrow, if possible, start playing Schnapsen. Get a glass of beer, get someone, explain the rules to this person, and start playing Schnapsen, because you need to understand it. Probably this week is too short, so let's do it for next week in any case, so that we get these numbers up to the hundreds. And why in God's name do I want you to play a card game. And this is the explanation. So this is the game environment that one of our students has written 2 years ago, in which you can build your own intelligent agents against you, and you can play against it and show your Schnapsen skills. So I've prepared this. So this is my command line in which I've started with all these things. Oh no, this is the command that if you download the game engine as it's explained on the course page, then you have a part on visualization. You just have to start a Python server against which holds the intelligence against which you play, and you have to tell it against which opponent you want to play. And our deep is one of the intelligent agents that we give you. Yeah, so that is now started at the back of my computer. It runs, and it has an interface on a website, which I will also show you. And this is this one. It has this weird name, 127.001/5000. And this is where this machine now waits for you to play Schnapsen. And as I said, it plays now against one of the intelligent agents that we've written, that we've provided, that you have in your distribution. But at the end of the course, and particularly at the end of the June course, you will have your own intelligent game played. And the idea is very simple. You have a pile of cards. So these are 10 cards. One of them is open, and that's the trump card. So it's the heart that is trump in this game. And there are two phases to the game. The first phase is that you have 5 cards, and they are not open to you. They are not open to your opponent. So this is the 5 cards that you have. And in the first 5 tricks that you play, you have to play a card. So in this case, I start. And your opponent doesn't have to play the same color. Yeah, so it's a different game in the second half. So you want in the first half, you want your opponent to get as few points as possible. So I start with this one, for example. I submit the move, and now it's the AI that makes the decision, and that takes the 12 points that you get for this. And what happened as well is now, after this part of the game, we both get 2 new cards from the pile. Yeah. So in the second phase of the game, in the second trick of the game, we both have 5 cards again. So now he played this card. I can win it, and I will quickly move through the first 5 tricks, because then you will see what happens then. So now it's my turn. I play this card. There is a special thing that I can announce, and that's a marriage that gives you extra points. Then I choose this one, and the game continues. So I continue until the pile is gone. So let's be quick here. Submit the move. So here above you see how many points I get. So now I have to submit a move, and now we've come to the second phase of the game. Yeah? So the pile has gone. There's no cards to get back anymore. And a very important thing about this situation that we're in now is that if you counted correctly, which of course you have all done, you know exactly which cards your opponent has. Yeah? So in the beginning we didn't know which card the opponent had, but now we came to a moment where we know exactly what the opponent has. So we've turned from a situation where we have imperfect information to a situation where we have perfect information. And now I can, in principle, systematically calculate all the possible ways this game will continue. And this is what we're going to learn next week, how you make a machine do this, namely find the best strategy for playing the next card if you have a perfect information game. And in the next weeks after, we move to techniques that also help us for the first week. For the first phase, where we don't have perfect information. Yeah? So now the game is almost over because I have 56 points and my opponent 52. and the opponent played the card, and I now have to follow. I have to now play the right color. I submit this move, and my opponent wins. I can tell you that this is a relatively straightforward bot, as we call it, agent, intelligent agent that we implemented here. I will explain it in 2 weeks or so, how it works. But it's damn hard to beat. So even if you know very well, if you can implement clever techniques, clever rules, it's very difficult to beat this very simple bot. And in period 6, so when the first year is almost over, we'll have a project in which you have to do research on what kind of AI technique do you need in order to write the most powerful and the best performing AI to win in these games. And don't get me wrong here, this is a very simple game. So it has 20 cards, 5 of them are open, it has 10 tricks, and still there is no machine that consistently wins against humans. So in that sense, it's a more difficult problem than the AlphaGo problem. And that has to do with the fact that it's an incomplete information game. So because we don't know what in the beginning actually happens, what cards are where, and that makes it a very interesting game to play. There are publications in the best AI conferences on people who try to write these kind of agents. And this is going to be our sort of example of building an AI intelligent systems in the coming weeks. So that is why it's very important if you really try to get a bit familiar with this game. So much for this. So I already mentioned some of those properties. It's an adversarial agent setting. Adversarial games will be covered next week in the lecture on Wednesday. It's imperfect information game in the first phase, and that makes it incredibly complicated. And what Google did for AlphaGo, we do now for Schnapsen, and obviously we are not going to solve it with high probability because it is a very difficult problem. But we want to understand it better, and we want to use it for some research. In this first phase of the course, we are mostly teaching about the theory and the practical research and development we do in period 6 when you know more about programming and about the logics and so forth. So some of the ingredients of AI and intelligent systems already came along, and that are 3 main themes that this course also has. And the first one is search and heuristics. So basically what you had in this second phase of the Schnapsen game was that I had 5 cards and my opponent had 5 cards. I know what my opponent has if I have a good memory. So I can calculate all the possible situations if I play this card and he plays this card and I play this card and he plays this card. I only have to do that 10 times, and then I know whether I win or not, because I can just count the points. And I just have to do that systematically through all the possible options and actions that I can take. All the cards I can put and all the cards he can put down. Here you see this on chess, because the idea behind this is exactly the same. So you have chess, you have one board position, one state as it's called, and you have, let's say, 15 figures that you can move in different directions. So you have 20 different choices for going from this board to any other board in chess. Okay, so you have your 20 choices here, and then your opponent it's your opponent's turn. And he again, or she again, has 20 also different options where to move the figures. So you see that in chess already in the second move, you have an incredible richness of possible board positions that you can reach. So in order to win the first chess games, people had to control this search tree. And how do you do that? You usually use heuristics. Heuristics is human knowledge, where you say, okay, I have an estimation that this chess position is better than this chess position. And that is, for example, that if I know that if I have more figures than the opponent, then I usually have a better chance of winning the game than otherwise. But then the question is, what is the value? If I have the queen, then my chances of winning are higher. And these are rules of thumb or knowledge that I can formalize. And I formalize them in so-called heuristics. So that is the first part of the course. That's what we're going to do this week and next week. The week after, Michael will take over, and I think a most recognized part of intelligence is that you try not to make the same mistake all the time. So you learn from your experience, you adapt to your environment. And there are different ways of this adaptation. So you can sort of try to abstract away from a series of measurements into a different representation form, such as from measurement points to a function. So that's a different representation based on some data. You can also learn to recognize some concepts in the world. So this is the link to the knowledge graphs that Frank explained about. So you can look at something, and even if you haven't seen it before, if you know the main properties of it, you can recognize that this is a bird. Wow, well, how does it come? That's very difficult for a machine. And we're going to look into how this is going to happen in week 3, 4, and 5. There are different forms of adaptability, and we're not getting that much into them, like evolution, for example. It's a very typical example of a system that learns from the past experience and improves on this experience. And the last topic is the one that Frank gave the lecture about knowledge, where the knowledge graphs are only part of a way of representing knowledge. There is a lot that we can represent in some kind of abstract mathematical representations. There is a huge amount of written knowledge or semi-structured metadata available, knowledge available. There are, for hundreds of years, we're now looking at classification schemes, at Thesauri and so forth. And the question is, how can we make use of that in the building of our intelligent machines? There's also knowledge that hasn't been necessarily explicitly given by humans. So I can tell you every bear is a mammal. But there's also more knowledge, and that is knowledge that we can derive from the structures in which data, for example, is given. So we know, for example, network structures, and we can derive notions such as popularity on these network structures. And you all know that, you all use it every day in a search engine. The idea of PageRank, which gives you the highest ranked, most relevant website, what made Google what Google is now, is based on this algorithm, where you have an estimation of popularity via the structure of the graph. Where you have if you have a random walk algorithm, so just things that walk randomly through the graph, then the probability of one of those beasts arriving at the most popular nodes is the highest. That's the definition of PageRank. And there are different ways of calculating this nowadays. But this is the idea, that there is some knowledge in the structure that we can interpret and from which we can learn. And we're going to look into these kind of things as well in week 6 and 7 of this class. So the basic knowledge you will have at the end sounds very mundane. It's about state space representation. So let's take a problem in real life, like Schnapsen or driving a car and so forth. And can we make a generic representation formalism so that we can always use the same algorithms on them for all the various problems that you can face as an AI agent? And then when you do that, when you can describe a game such as Schnapsen or riding an autobus or whatever, then how can we find the optimal solution, the best to our problem that we can reach? And the answer is through search, and that is part of the first 2 weeks, what we're going to do in the first 2 weeks. We need a notion of agent. That's what I'm going to talk about today. So what does it mean for an intelligent agent in the first place? And then we're going to look into machine learning and knowledge-based reasoning. This is by no means a complete overview over what AI does and intelligent agents do. As I said before, there is planning, natural language processing, robotics, perception, scheduling. So there are many, many different topics. Some of them will come back in the curriculum in the next years, and some of them you will have to specialize in a master and so forth. But the basic skills is what we are going to look into in this course. In the practical part, we want you to start thinking of the Schnapsen game in terms of this state space representation, and then apply search and adversarial search in particular for finding the best strategy to play the game. As I already said, this works for the second phase. It works very well because it's a perfect information game. So the algorithms that I explain next week will really give you an optimal way of playing the game. But because of the first phase of the game, it's an imperfect information game, we need other methods such as learning strategies, heuristics, and some Monte Carlo sampling and so forth. And then there's also a lot of intuition and knowledge that we have as humans, so we can also try to see whether we can represent some of the human strategies in the game with some logical algorithms, some knowledge representation methods. And that's what I'm going to talk about in the last 2 weeks of the class. So the course will be about decision making in principle, because that is all what it all comes down. And it's not just a decision for a specific problem, but it should be efficient, simple, correct, well understood, and generic. We want to come up with algorithms and methods that we can apply on the one hand on Schnapsen, but in very similar ways, in principally understood ways, also for the self-driving car. That is what specifically is about the AI. We're not looking at one specific problem, but we're looking at the generic kind of intelligence or methods that you need in order to make some intelligent behavior. If you want to finish this course, which I think is, of course, one of the main objectives for you to optimize here, then at the end of the first week, you have to understand the basic concepts of what an agent is, what state space representations are, and what heuristic search is. And then you need to know the main algorithms, such as min-max algorithm with some kind of optimization, the famous A-star algorithm, which we're going to look into on next Tuesday. And you have to start to play around with these game engine. So I want you to at least to be able to play with this engine, to have the Python code installed, and then we have provided some tools, some bots for you, some agents where there's just one line of code missing. So you need to understand how this all works, and that is more complicated than what you know about Python and what you will learn in the first weeks. But I really encourage you to try to go through the code. It's well documented. You cannot break anything. If you've sort of messed it all up, you just delete everything and you download it again. So there's really nothing you can break. Play around with this. And that's basically the task for the next 2 weeks, I would say, for you to get familiar with this game platform and the way of writing these kind of things. And if you hear fancy words that you don't understand, such as object-oriented programming and recursion, just ignore and try to understand anyway what it is. Just go through the code and see what happens and calculate it through maybe with some simple examples. There will be 4 lectures, so 2 this week, 2 next week, and 2 practicals and 2 computer practical, working groups and computer practicals, and you should all be registered to each of those groups. There are some few people who've contacted me that they have been scheduled the same time. So if you're one of those people, if you would come to me after the lecture, not on the break, but after the lecture, that would be good. Then we can see what we can do for you. Yeah. In the second week, the principle is the same. There's one more lecture on uncertainty and machine learning. In week 3, 4, and 5, there are again 2 working groups and 2 computer practica to get you going on this. And the idea is that you understand the main concepts of approximation, how to deal with uncertainty, how to deal with the fact that you do not know what cards your opponent has. And again, there are principled approaches for doing that. And then, of course, it's about the basic concepts of machine learning, the main idea with learning with the neural nets, and maybe some basic ideas how to train a deep model and so forth. Again, there will be an assignment for you to implement an adaptive agent, and this sounds huge, but it's relatively small. And Michael is going to explain that, how to do that in 2 weeks, so don't worry about it. And again, then in the last week, I want you to also look at some aspects of knowledge. How can we look at human rules in order to help to make our intelligent agents even more intelligent by telling him some kind of strategies that he might or might not apply. And again, so there's a lecture less than for machine learning, because we also want to spend the last lecture on ethical questions and on philosophical questions of AI, because that should also not be forgotten. And we'll also provide a test exam, because what you will have to do is pass, and that's the main part of the course, the digital exam, which I think is on the Wednesday at the last week or so, but you have to look it up. So the exam counts for 75%. So this is really the core of what you have to do. And basically all the theoretical material that I explain in the lectures, Michael explains in the lectures, and that we are practicing in the working groups is also being asked in these digital exams. There's a test exam, a practice exam, so that you know what kind of questions you can expect. And I think if you really come to the working groups, the theoretical working groups, where you practice all these questions, I think you will be fine. That would be my advice. Come there, or at least look at the questions. There will be solutions to the questions as well. And if you think you do this better in your own time, that's your own decision as well. That's fine. And you will have to do this for all the topics that I just went through. As I said, there's also a practical part, and that is on programming. And as we know that several of you do not know how to program, it would be extremely unfair if we would score you on your programming qualities unless you had the chance to learn it first. So the way we want to do this is that there is a set of worksheets on which you have to work, and you have to try to make implementation. And the way, what you have to do is to keep a log and tell us what you do in order to try to solve the problem. So which were the types of code that you wrote? Just give a good motivation that you tried hard, and if you tried hard, then you will get the points. There will be no grading for these worksheets. Either you get them or you don't get them. There will be 10 points for the machine learning one and 10 points for the search one, and 5 points for the knowledge one. And you need half of the points. So you need one of the big one and the small one, or two big ones. So you need two of the three. Basically, just submit something that summarizes the work that you have done. We haven't done that before, so it's also a leap of faith from our side. The idea is that we really want to encourage you to get onto the programming, write code, try it out, talk to the TA, so you have lots of opportunities. So that you know what is important and also what needs to be done. And maybe it comes at the end again. I can't remember whether it's at the end again. But if it comes at the end, you're allowed to leave. Yeah? So what the lecture today is about is what is intelligent systems and what is this course about. So I think that is the part that we have now done. And then the part that is still to come, so you see there's a lot of stuff still to come, is what are agents and what is rationality? What is the role of the environment for how we have to design agents? What type of agents are there? And then how to model problems at state space problems. So that's the last thing we want to do. And as I said, there is a bit of homework for you until tomorrow, but probably more until next week, and that is play snapseed. Yeah? So that is my homework for you for next week, so that when I talk about the rules and the complexity about it and the algorithms that we need, that you understand what I'm talking about. Yeah? So this is my summary of the lecture and also my homework for tomorrow. So now we can go on with the lecture, and I hope that I get done in time. So intelligent systems, I use a little bit inconsistently this term, and it's sort of building intelligent agents. So we always talk about also intelligent agents. I think the important part is that it's a subfield of AI in which we look at the technical part of the agent. So we don't look at the cognitive side of how such an agent works, and the social part of what is the role of an AI in society or in communication with other people and so forth. So there will be other courses. There will be course robot interaction. There are dynamic modeling courses which is about more the role of knowledge and how can we enrich our agents with implicit human knowledge. Now this is really about the core algorithmic part of AI. So this is, I think, the distinction between intelligent systems and AI that I want to make. Don't make a distinction between building an intelligent agent or an intelligent system. That is more or less for me the same in this course. The building of an intelligent agent, we had these discussions in the previous course. What is AI? And we had these sort of definitions by Turing, a system that can perform in a way that it can't be distinguished from a human in certain perspectives. We put that aside. So we take a relatively technical definition of what we want to do. What does it mean to build an intelligent system or intelligent artificial agent? And that is, we want to build a rational agent. And the notion of rationality means that it chooses actions that help him perform as good as possible with respect to some goal that it has, based on some percepts that it gets from its sensors and knowledge that it has. So this is going to be our working definition of what we want to achieve. So there is no omniscience, there is no perfection involved, but there are very clear notions of a goal that you want to achieve. And you can put that in your agent in an explicit way, in which you say, okay, this is the goal that I want to achieve, and these are the rules that will help me do that. But there are also more complex ways. And we're going to talk about that a little bit. So the way you can think, and these are all images from the book, AI, A Modern Introduction, a Modern Approach, I think, from Russell and Norvig, the Bible of AI. So I don't know whether you bought it, but it's a beautiful book, 1,200 pages or so, and it covers all the aspects of AI that you will see in these next 3 years. So if you want to invest in one of the books around, then this is really one. And basically the course, also the structure, is based on the way that Russell and Norvig introduce intelligent agents. And also the way they present it here. So the idea is that you have some thing, whatever it might be, and this thing has a set of sensors which helps perceive things from the outside world in order to take some decisions and then take an action. This sounds very simple, and it is very simple. So it has one way of or two ways of communicating with an environment, whatever that might be, namely perceiving some things with the sensor like an eye or a measurement thingy, and it takes some actions. It can walk, it can blink, it can. Now, let's look, for example, at this thing. This is in its very simple way. It's an intelligent agent. It measures the temperature in the room. It has a very simple, probably hard-coded or even mechanical rule in that if the temperature is below some certain grade, then turn on the heating. So basically we have the environment, which is the room. It measures via some thermometer or whatever it is. It measures the temperature. It has some decision-making algorithm, and it takes the action of increasing the heat or decreasing the heat. And there are different ways of looking at that. We can look at the problem, the actual problem, where we have then the intelligence of the agent defined in a mathematical way, so just the function from the states to an action, so to the perceptions, all the perceptions that it gets, the percepts it gets, it takes as the input, and the output of the function, the intelligent behavior, is then just an action that it takes. You can also look at this, how is it implemented, the agent program, the actual program, and then it might come in a physical infrastructure down here. So these are three different abstraction levels that we can talk about these abstracts. And then we come back to the notion of rationality. As I said, it's about maximizing the expected value of the performance of your system according to the knowledge and the percepts that you have. And then it really depends on what kind of measurement you have and what kind of expectation you have. And here we come back to the notion of heuristics. So you want to expect, you want to measure or estimate the expected value of your action, the state that you get after doing some action, and that's a guess. We don't know. The machine doesn't know what will going to happen if it doesn't takes a certain action. Then we can look at the different actions and the choices. Where does it get us? And if we know what the next steps are according to a certain action, we can systematically look at all the possible states that we could get in. For example, in the snapseed example, we can put a card, then we can see, we can observe what our opponent plays, and we can act again. And then on all these actions that could be or could not be taken, we can have a systematic search in this problem space. We can learn from them, and we can use prior knowledge. There all these elements come back that I've been talking about. Rationality doesn't mean that the thing knows everything. It depends on the environment. It knows some things. It can only measure things in a certain environment. And it's clearly not striving for perfection, because that doesn't really make sense. What it is important to study, though, is in what kind of environment are we talking, and what kind of problem are we going to solve, and how does our intelligent agent need to deal with these environments. And there is a method described in the book, and that is that you have to look at, if you design a rational agent, whatever it is, you need to study exactly what kind of performance you want to achieve, what is it supposed to do? We need to look at the environment in which it operates, what do we want, where do we want it to operate, and then the two things that I've mentioned already, what are the things that it can do and what are the things that it can measure, what can it perceive. So these P's acronym for this task environment. And we look at this into a bit more detail. So if you have, for example, a taxi, an automatic taxi, suppose you want to travel with this or not, and then what do you want this autonomous taxi to achieve? You want it to bring a person from a certain place to another place, so that is really the main functional requirement to this thing. So get me from point 1 to point B, but then there are many other measurements of performance that are important. So the safety, is it really the right place that it gets me to? Does it cost $1 million to get there? Does it is it legal in the first place? And how comfortable is it? So it's not only the functional requirement, but also the more softer performance measures that you can take into account and often have to take into account. Then what kind of environment does it operate in, this taxi? It's the streets, it's a freeway. It also has to take in this environment into account that there are other cars or people or bicycle people, pedestrians. It might have to take into account the weather. If there's snow, then it needs to behave differently than if it's a dry street. And then we have the actuators for such a car. You can steer, you can accelerate, brake, push the horn, and so forth. And the sensors that these autonomous cars have are cameras, sonar, speedometers, engines, keyboards. You can have direct contact via keyboards, GPS. You think about it. This is all where the information comes in for this thing to operate. And this is what sort of defines the task that we have to implement if we implement an intelligent agent. So here are some examples, and we are going through this list systematically. And there are some criteria that you can apply to those generic problem classes and try to understand what your specific problem belongs to. And one of them already used quite a lot with the Schnapsen game, and it's important to really look at those things more systematically. So there are four examples. The first one is a solitary game. Then we have the gammon. Then we have the task of helping you to find something on the internet, to a shopping assistant, and as I said, the taxi that we've just been talking about. And now there are different criteria that we need to understand whether these problem classes belong to or not. The first one is fully observable versus partially observable. And that means that do I have all the information about the environment? So can my sensors detect all the aspects that are relevant for the choice of action? So if we talk about the solitary, then of course all my cards are open. I have to see, yes, they are. For the gammon, it's also, you know which stones are on the table. So it's a perfect information game, but you have the uncertainty about which dice, what is the outcome of the dice. But all the information that we have at the moment is available. For the internet shopping, it also more or less is that we know a lot, but there's also loads of parts of the internet, of the shops that we're not aware of, and the taxi, of course, absolutely not. So you have some partial observability. Here you have full observability. You know everything that you can know about the game. There's just an element of chance involved. And that was the notion that I already used for the Schnapsen example. So that was observability versus non-observable or partial observability. Deterministic is the next question. So we have the choice between deterministic and stochastic. So the question is that if you take an action, is it known in which environment you end up? Is there only one, deterministic, environment that you can know that you end up with. And so if I play a card in solitary, then of course I know which the next state is. So I know where the card lies because I put it there, and it's there. Nothing changes about the information that I need about this game. In backgammon, it's the same. So I play my stones, and then I'm in a new state, and then there will come some aspect of stochastic, some chance in the game of my opponent. In the internet shopping, there is in principle, whenever I take the action, I search for something, I always should get the same result. That is not always true, but I think there is some kind of mostly deterministic behavior. And for the car, again, there is no idea what other impact might have someone who comes in from the side, other cars, and so forth. So I see that I explained the backgammon wrongly, because the way this is in this table means that the throw of the dice is determining the next state. So I thought in the transition from the states, it would mean I put my stones, and then but here, the answer that you have here means that the transition includes the throwing of the dice, so this stochastic element is in here. Sorry for that. So this is correct. Because you throw the dice in order to get to the new state. Then we have the question whether the environment remains static or whether it changes. So if you look at a chessboard and you decide to move your queen, and then you realize that suddenly the board is completely different because your opponent has changed the figures, yeah, then this is a different game than the one that you have your strategies for. So in chess, it's clearly that the environment doesn't change, and the same holds for solitary and backgammon. In internet shopping, it might be that your assistant, intelligent assistants, gives you some offers, but they have been disappearing on the side because so many things happen on the web that it becomes almost dynamic. And the car, of course, driving is a very dynamic environment where so many things change. There's people on the street that cannot be predicted in one way. There are two more to come. The screen versus continue, and that is whether you have a finite number of possible outcomes of an action and a finite number of perceptions that you can have. So if you can, so the trick is if you can count the outcomes of your perception, then you are in a discrete case. And if you have to measure them, then you are in a continuous space. And clearly, the solitary game gets you to a number of possible states, and there are a number of possible things that you can perceive. The same in the backgammon. Again, the only example where this is far less given is the taxi. And the last one is the multi-agent versus single agent. So here we have a situation where we have only two, maximum in this course we only deal with two, maximally with two agents. In the real case of an AI agent, multi-agent scenario is obviously also very important, and there is a special course on that in the second year. So solitary is a single player game, so you go from one state to another, nobody else interferes, and all the other cases, there are some other people involved. So in the internet shopping, someone else might have a bid for some object for a better price and so forth. So this is the information for Schnapsen. And I didn't want to give it, but I did wanted you to try this yourself, and I have another Menti for that. So if you could go to the same side again, have downloaded the slides and look at the slides at the moment. You're not allowed to participate because the answer is in the next slide. So the question is Schnapsen fully observable? So can I ask one of the 9 people who voted for yes? Why do you think who voted, who said yes? Can I ask? No shame, nothing. Can you? There's 12 now. So who of the 12 wants to explain why you said it's fully observable? Okay. So my objection against the full observability would be that there's a pile of cards where you don't know what's in there and you don't know what your opponent has, what kind of cards. So in that sense, I think the no answer is the correct one. Is Schnapsen deterministic? So is there always one state you get into according to one action? Next time I should get one where I don't show the progress and only show the progress at the end, because I think there's some preferential attachment, I think is the word, that you are more likely to vote for something you see is the right answer. So congratulations to these people. You did really well. You have your own opinion, and it might not always be the right answer, but I think it's very good that you gave it. Next time, so I agree with the people who said yes, it is deterministic because we have a certain set of cards. If you play one card, you get into one clear new state, and there are no other possibilities. So you can't end up in uncertainty in which state you end up after you play the card. So I will skip now because there's all of those. Think about this in more detail because this might be something. Yay! Congratulations. No, let's not do that. So it's not. Okay, so this is my answer. I hope it's correct. Is that more or less? It's not fully observable. It's deterministic. It's static because nothing changes in between the moves. It is discrete because I only have a finite number of actions that I can take, and I have a finite number of information bits that I can get. And it's not single agent because you play against another agent. Okay, the impact of these environments is very important to be aware of, that you really understand what is it you have and what is it you don't have in terms of information, in terms of observability and so forth. And as you can imagine, the more complex your environment is, the more difficult it is to develop an intelligent agent. Yeah. So the simplest one is fully observable, deterministic, episodic, static, discrete, and single agent. But more likely, you will build an agent that's partially observable, stochastic, sequential, dynamic, continuous, and multi-agent. But many interesting AI problems don't have that full spectrum of complexity of the problem. So this is the place I thought I would get before the break. So that was my summary slide. Now we have looked at what kind of environments do these agents operate in, and how do we have to design? That's always the question. How do we design an intelligent agent for a certain environment? And that means we need to study this environment very carefully so that we can design the agent properly. So here is a very quick overview of different types of agents that you can have and that you can build. We have the simple reflex agents, which basically just have some direct contact with sensors from the environment. They have a state, a situation, how the world is at the moment. They have some condition action rule that, based on the input from the sensors, determines a direct action to take, and it takes this action. So it really is like the heating device that says if the temperature is lower than 25, don't do anything. If it is higher than 25, start the air conditioning, whatever. Yeah, so that's a very simple type, and it's quite powerful already. And so next week, some of us are going to the field trip, and most of the things that we're going to build are these kind of simple reflexive reflex agents that just measure something and then take some actions. Yeah? So if you haven't registered yet and you want to go, please do so, because we have to close the registration very soon. I will also send more information about it soon. So in the book and also in the slides, there is Can we continue, please? You will have plenty of time after the lecture to discuss this. Guys, please. So, you will see on the slides, and I sometimes go quickly over the pseudocode that is given there, but it's very good after the lecture to look at the pseudocode that's given, because that gives you an algorithmic feeling to what we're doing here. And so here it's very simple. You have some percept, you give it some interpretation to your state. You have the state and a certain rule as an input. You check whether the argument of the rule is fulfilled, and if it is, then you take the action that fits the rule and you return the action. So that's basically the decision procedure of this reflex agent in some algorithmic way in a pseudocode. Obviously, this is in many cases it's not sufficient, because you also need to model some state of the world in which you're in. So you have these reflex and state agents, where the state means that you have a representation of the world as it's now, and also how the world evolves and what the effect of a certain action would be. So basically you take the same idea that you have some input, you measure the temperature in the room, but then you also think, okay, if there are now 120 people in the room, and if in half an hour they will all be gone, then I don't need to switch on the thing now. So basically you take into account some interpretation of the model of the world. And then you take the condition action rule, and you return, as your intelligent behavior, you return in your agent function, you return just the action that you want to take. And again, so you have a bit more in your pseudocode, you have a bit more complexity, but in principle the idea is the same. What we still haven't had yet in the model-based ones is in the previous one is that we also have a choice of going somewhere according to the notion of a goal. What do I want to achieve? And these are then the goal-based ones, which obviously come far closer to the notion of rationality that we've been talking about. So basically, you really need some notion of search now, because you want to know how, in your state, you know how the world is at the moment, what the state of the world is, and what would now happen if you take a certain action and does it bring you closer to the goal that you want to achieve or not. And then the goals help you to choose the right actions according to your perception. And then you can turn all of those into learning agents where you also have some kind of feedback, probably, and you try to improve your action choosing mechanism based on the feedback and on the knowledge that you get from the sensor. Yeah. So these are two important elements of what we need to take into account when we build intelligent agents, namely in what environments do they operate and what kind of agent do I need then? How much information about the world and the states do I need to have? Now we come to the sort of last part of the lecture, and that is how can we come up with a generic problem description structure in which we can represent all these kind of problems that we've been talking about and generalize so that we can look at generic solutions for these kind of problems instead of solving all the little ones time by time. That's I think, the specific thing of AI, that we look at these problem classes and look at intelligent ways, rational behavior within these problem classes. So let's first look at how can we represent these kind of problems that we've been talking about as state space problems. And you can think of a very simple but quite complex still example, and that is the intelligent Hoover that you have. And the intelligence, now we're not looking at the technical details. So this is a rather complex thing because it has a motor, it is in a complex environment, it doesn't know whether there are stairs. So if you think about it, it is very complex, and if you would want to model all the problems that this machine can have, you will have to write an incredibly complex problem solver, an algorithm. So what it makes sense is to look at the specific parts of the problem and how to solve those and how to address those. So we're now looking at a very, very simple part of the problem, namely not how to make this thing move and how to make to measure how good it performs and so forth. But we just look at a part of the thing, namely how can I decide in which of the rooms I'm now cleaning. And that is already quite powerful because most of these these Hoovers or gas machines, they are walking randomly through a room, and that's sufficient to clean them if they are long enough in the room. But deciding in which room to be is maybe quite a useful thing to do. Do you mind keeping it a bit... Okay, thanks. So the decision of where to Hoover is something that we can model as a specific problem. And this is what is done here. So we have a very simple element of this problem, namely just two rooms. And what we have is, there is some dust. We can measure whether there is some dirt in the room, and we know where the Hoover is. And we can now model this. The world itself is incredibly, absurdly complex, but we can reduce it to a relevant problem where we can write algorithms for solving this. So we can now translate this problem of hoovering into different rooms. We can translate that into an abstract mathematical model, which is called the state space model. It's rather complicated to concentrate if there's such a rouge, I don't know what. So can you do me the favor and stay quiet for another 15 minutes so that I can concentrate and your peers can concentrate? Yeah? Please. Yeah. So what we want to do is to abstract away from the complexity of the real-world problems to some mathematical representation of the core of the problem for which we want to come up with generic algorithms. So basically, if you have an action such as move from this room to the left room, then this is a summary of loads and loads of complex actions that this machine has to take. So we abstract away of the technical problems to just one part of the problem given a certain level of abstraction. And then the outcome, of course, is only on this abstraction level as well. So the solution is a set of real paths that correspond to the solution in the real world. And there are very often different kinds of representation of the same problem. Yeah? So if you think of this, if you look at the Hoover example again, then we have only two rooms. We only have two states in which the room can be, namely dirty or not dirty. And we have a set of actions that you can take. So basically you can take the entire decision problem of what do I have to do, where is my robot, and where would it clean the room. The whole problem can be represented in this abstract state space. So here the state says that the Hoover is on the left-hand side, it's a dirty room, the other room is dirty as well. And all the actions that the Hoover can take is going to the left. If it gets the action, take the action, go to the left, it ends up in the same room, so it does nothing. If it gets the action, go to the right, it ends up in a new state. It's a new representation of a state. Namely that this room is still dirty, this room is still dirty. It is dirty, but the Hoover is now on the right-hand side. And now we can have, if it just sucks and cleans the room, then we end up in a new state. And this is obviously a graphical representation, but I can also write this down as a mathematical object of just saying, okay, the left-hand side is still dirty, the right-hand side is still dirty. Yeah? So basically what we've now done is that we have reduced the very complex problem of how does a Hoover clean more than one room by deciding where to go to this mathematical problem that we now have to solve. And basically the task then becomes that if I am in one of the certain states of this certain space, how do I get to one of those places where both of the rooms are clean? Because this is the goal that we want to achieve. And now it is up to our robot to have enough intelligence within this state space to decide how to get from this state to this state. And what this basically gives you is, if you just first clean the room, then you go to the other room, then you clean again, then you will have a clean house. And this path is basically a set of actions that brings you from the state you're in, the initial state you're in, to one of the goal states. And the only thing we need to do then, and that's what we're going to look into tomorrow, is how can we write algorithms that help us from this starting point to get as quickly to some of the goal states that you can have. Okay. So that is the generic picture that I just described. We need some kind of abstraction for our problem, namely represent states, initial states. We need to decide what the actions are, and then next time we will also look into what the costs are. We need to know what the goal is, and these were, in this case, the states where both of the rooms are clean. These are our goals. And then we need to determine what are the possible sequences of actions that bring me from the initial state that I'm in to one of the goal states. And then, in the end, we give this decision that was taken, namely the set of sequences, the sequence of actions, and that is then our action to clean the house. And that is the intelligent behavior of this agent. So the same idea can be applied to robots, for example. So this is a very simple representation of an assembly line where we have the robot arm in a certain state, and you probably can choose here whether you want a discrete representation, so just 2 positions the robot can be in, or a non-discrete one. But in this simple version, let's say we have certain actions that we can take. So here is a rotation area, here is a rotation area. This can be made longer. Here we can rotate, here we can rotate. And we can now abstract away from that. So which of these actions would you need to take in order to get from A to B, for example? So in this case, the states would be a description of in which angle do we have this, in which angle do we have this, which is the length here, which is the angle here, the angle here. And that would give me a description of the state we're in. And as soon as you take an action, so for example rotate, you would get a different angle, you would get a different position for the arm to catch. And then the only thing you have to do is look at all the possible movements of the arm. So how do you deal with this? If you get a problem and you want to translate it into states problem, you have to start with this problem and formulate some abstract algorithmic versions of this, in which you leave out some of the complexity that you don't want to deal with. So formulating states and formulating the possible actions to get from one state to another one. So in this case, for example, clean the house is the goal that you want to have. So you want to reach a representation in your state space in which both of the rooms are clean, or you want your robot arm to be in a certain fixed position, whatever. And then the task is finding the solution by search as a sequence of actions to get from these initial states you're in to the end states. And then, of course, someone needs to execute this plan, but this is a sort of a different task. Here's another example. This is a representation of a map in Romania. And the task is that you are in one of those cities, in Arad, for example. You need to catch the flight in Budapest. How do you get there? And how can we represent this problem now as a state space problem? The states, in this case, you could say that each of the cities in Romania, you being in one of the cities is a state. moving from one city to another one brings you to a different state, and you being in a different state. And look that these are, of course, abstractions from very complex problems. Namely that in order to get from Arad to CPU, you only have here, okay, it's 140 kilometers or something. But obviously, these are roads, there might be traffic jams. So there's a lot of complexity in the environment that we have taken out here by just saying, okay, it takes you 140 minutes, kilometers, whatever it is even. And all the question of how do you get there is abstracted away. And still, it's a very important and difficult AI problem to find the shortest path between Arad and Bucharest or wherever you want to go. So again, we have to look at a concrete plan. You want an Arad, fly tomorrow to Bucharest. You have to find the abstraction. The abstraction is a map that I just showed you. You have to formulate the concrete goals. So the state where you as an agent are in Bucharest. In Schnapsen, this will be one of the winning states. You need to find a solution. So this is the sequences of travel that you would take from Arad CPU, Făgăraș to Bucharest, for example. And then in the end, you have to, some different algorithms will have to buy the tickets and travel physically. But this is not part of the algorithm here and the problem that we're dealing with. The same, and that is the power of what we're doing here, is that exactly the same holds for the games that we're talking about. So if you are in chess, as I said, you have a state, and the state for the chess is just where do the figures are? Where are the figures on the board? And you can think of that as a mathematical object. And then we have an action on one of those states, namely move one of the figures. And that gets you to X new states that you could be in now, that the board will be in. And the goal state, or goal states, is one where the king is just made. And the finding the solution, the strategy for the game is finding a path from the situation that you're in to one of the boards where the king is just made. And obviously in chess, this is more complicated because we have a state, an action, where once you take the action and in the next move the opponent takes an action. So you only control half of the actions. And that's what we're going to look into next week. So I have still too little time. But I want you to think of it and look at it in the slides. Till tomorrow is probably too short, but still I want to explain it and I will take it on tomorrow morning. So we now take a very, very simple variant of the game, of the Schnapsen game, namely where we only have one player. And this one player has 5 cards, and it can just play these cards, and it sums up the values of the cards that he or she played, and she needs 22 points in order for the game to finish. So this is a very stupid game that if you have 5 cards and you just play the highest cards, you know that you win. But for a computer, that's not so obvious that this is the best strategy. So if you look at the game now as a state space representation, you see that we have
Okay. So the machine learning under intelligent system. And this will be our references. Okay, so this will be the references of our discussion. So thank you for attending the class and see you next meeting. Good day, everyone.